talk, and this is by John Keller. He's going to be talking to us about the LRO Mission After 6 years, what we have learned and what we have yet to learn. Welcome. I will give you a 2-minute warning.
Okay, thanks. Let's see. Okay, well, it's good to be here and to kick off the first of the mission talks. LRO has been with the Survey Forum and before that the LSI Forum really since the beginning, and I like to think of LRO as the virtual partner to the Virtual Institute. And I hope to show I'll show some examples of what I mean by that as we go on. Always show this 7 instruments on LRO. Many of you have seen this, of course, but I assume there's some new folks here. So we have Crater, which is the radiation instrument on the spacecraft. Diviner, which measures the temperature of the surface of the moon. Lola, which is a laser altimeter, measures the topography. LROC is 2-camera system, 2 high-resolution cameras, and then color wide-angle camera. LAMP, the Lyman Alpha Mapping Project, LEND, the neutron detector, and finally a mini RF, which is the radar. So just some key dates. As I said, the first NLSI forum was in 2008. We were in the process of building the spacecraft then, launched next year, and have been in the mood for 6 years. We're in our second extended mission, which will end in September of next year. And then there's a possibility of a 3rd extension, and we're working on that now. We're in the process of coming out with an ICRA special issue. We have some vigorous response to that. A lot of papers have been sent to the issue. We're very pleased. We do have contributions from the broader community, and not just the LRO team. The submission deadline is passed, but if something were to come in before the end of this month, it stands a good chance of making the issue. As a result of this, and there will be a large pulse of requests for reviews, and many of those requests will come to folks in this room. So I encourage you to accept, and it'll be great help if we can get these papers through. So just a little bit about the LRO orbit. So the chart on the bottom there shows the periapsis and apoapsis of the spacecraft through the mission. And early on, we went into our 50-kilometer mapping orbit, which is this here, shown here. Periapsis has been consistently over the South Pole, and then this was an orbit that was expensive to maintain, and we eventually went into this more elliptical orbit, but we still have a periapsis over the South Pole. And so as a result of that, we get many high-resolution measurements over the South Pole. So LRO is very much a polar mission. I have lots of data on that, and I'll talk about that as we go forward. I'm often asked the question, how long, it's the most common non-science question about LRO that I get is how long can LRO last? So this is the long-term prediction of the orbit and out to 2024. And so if we did nothing with the orbiter, instead of it eventually crashing, it just seems to get more circular. So what happens beyond that, I don't know. And the answer to the question is how long can LRO last is, again, I don't really know. And probably it's not constrained by the orbital dynamics. we went into the mission with a polar orbit, but slowly with time, the inclination of the orbit is changing, and it's going down. So here's another long-term trend, and you see the inclination is now about, averaging around 87.5 degrees, and the slope here is about half a degree per year. So this is has a bit of an advantage for us in that we've pretty much saturated the South Pole and the North Pole with measurements by virtue of many passes, and now we're able to expand this sort of high resolution, high density measurements over lower latitudes. So we're in this second extended mission, and these are the themes: transport of volatiles, contemporary surface change, regolith evolution, probing the interior from observation of the surface, interactions with the space environment. And I'll just say a few, I'll just give a few charts on some of these. Starting off, the question of volatiles, especially over the South Pole. So early on in the mission, the LAMP team found evidence of water frost in permanently shadowed regions. And now as the mission has gone on, you see a lot more studies that combine data from not just inter-instrument data sets, and then also with other mission data sets. And this is an example with using Diviner and LAMP to further constrain and understand how frost could be put into these permanently shadowed areas, and based on the temperature, what would constrain that. Another example of inter-instrument observations is this one from the LOLA team and again the Diviner team. So LOLA is looking at the brightness of the return laser pulses going over PSRs, in this case over the North Pole, and you see that you see this increase in brightness. Well, that alone maybe doesn't tell you much, but when you see this correlation between this brightness when you're going over permanently shadowed areas where the temperature is very low, that at least is a clue that perhaps there's some volatiles, highly reflective surface frost that may be contributing to that signal. So that's part of the story. Another example of LAMP, recent LAMP measurements is one that, again, early on, LAMP discovered that in these PSRs, the albedo is dramatically lower in the far UV. And the explanation has been suggested that perhaps it's due to something unique about the PSRs where the regolith is fluffier, may have this fairy castle structure, and absorbs light much better than outside the PSR. And further evidence of that now is discovery what looks like to be recent impacts inside PSRs. And now this signature, this is kind of a unique and new signature for a recent impact, is simply that this fairy castle structure during the impact is compressed, and then you get back your original characteristic albedo. And so it's sort of a kind of a combined new method for dating recent craters and helping us to understand what's going on inside of these craters. Well, why would there be more fairy castle structure inside the PSRs? One possible explanation is given to us from the crater team and also from the NLSI or the survey DREAM team, and that is this breakdown weathering may be comparable to meteoritic weathering. So inside these permanently shadowed craters, they're very cold. One characteristic of the very cold environment is that the conductivity is reduced. Electrical conductivity is greatly reduced, and therefore charges can build up, and you might start seeing deep dielectric discharge, or just the very large charge building up and sparking over and creating these events that over geological periods of times may lead to this increase in the regolith porosity. And also the surface of these PSRs, there are electric fields in there which may be very high compared to outside, where you have sunlight, which through photo emission reduces the very large electric fields that may exist inside the PSRs. Another recent example from the LEN team of the Shoemaker crater. This is a new map of Shoemaker crater of the neutron suppression, which is an indication of hydrogen inside these craters. So early on, when we went to the moon, the expectation, at least that many of us had, was that if there is water inside PSRs, it would show up in the neutron data, and it would be. But what we have found is that not all the PSRs have this indication of neutron suppression. Some of them do, and one of the strongest one is it comes from the this LEN map. And you notice about this LEN map is that in Shoemaker crater, it's strongly on the poleward-facing slope that you see this neutron suppression. And that's a characteristic that the LEN team has already found in general, that poleward-facing slopes have more neutron suppression. And the explanation from that is that, well, it's tied perhaps to temperature, and when you have these insolation conditions, that there's a slight variation in temperature when you have a poleward versus equator-facing slope. That seems very logical, but here we have Shoemaker crater that's in a PSR and doesn't care about where the sun is, because the sun isn't getting in there directly. And so that's a mystery here that is an open mystery that we would like to see explained. Perhaps it has to do with the emplacement of the hydrogen at some time in the past, when the spin axis of the moon had been changed. It was not where it is today. Oh, okay. Okay, I'm not going to get through all this talk, but let me in the question of PSRs, not everything we've done points to surface frost, water in the surface of these PSRs. So the LRO team is able to image inside these PSRs and has found that has not been able to find an indication of surface frost on the visible imagery. And this is in contrast with the Mercury Messenger mission, where they did find indications of surface frost. And so that is one of the big questions we have from a comparative planetology point of view. We've shown this before. This is an example of LROC observations of changing of impacts on the surface of the moon. And really, this is an opportunity to really dig down into what these impacts are telling us. And you can look at this particular March 17 impact and just start looking at the ejecta and what is happening there. So these new impacts are a new tool for studying ejecta, studying the surface. And the team has found numerous of these craters throughout the moon. And what's interesting is that the ejecta patterns are very different in some cases. Well, what is that telling us about the regolith and the surface of moons at different places? And we need really to get as much of this data and much of these new impacts as possible, that maybe we can tell a general story of what's going on. An example of data that builds up and has told us a lot given time. So early on in the mission, we see these thrust faults distributed throughout the moon, but that's an indication that the moon is shrinking, still shrinking. But further analysis shows that these thrust faults, their directions are not randomly oriented. They're actually oriented with the force fields associated with the orbit of the moon around the Earth. So just a couple of examples of the partnership, the virtual partnership between LRO and the survey team. Sample sites within SPA and the ability to plan missions. Another polar South Pole study by the SEED team. And then a quick advertisement for the Lunar Data Analysis Program. We'd love you to analyze LRO data as well as other missions. These are coming up, step 1, step 2 on those dates. PDS is where we put all the LRO data. And then my last slide here is a fabulous new data set by the Lola and Celine team where they've combined the Lola data with the terrain camera data. See the poster, you can see the differences in the improvement in the topography from left to right if you look at the plus F, and you can learn more about it on poster 59. Thank you.
We have exactly 1 minute for questions. That's perfect. So come forward, come to the microphone if you have a question. Bill Bucky, can you please? We are trying to record. This is for posterity.
I think the slide, you said something, the slide had something very interesting, but I didn't hear a discussion of this. You said that the PSRs on the moon are very different from those on Mercury, but I wanted to hear more about what the differences were. So can you go into that?
Well, I was referring to the evidence of water in the PSRs. And so the Mercury data, from the beginning, we saw the strong radar signature in Mercury with an indication of ice in those craters. We don't see that on the moon. We see visible imagery in Mercury in that example, and we don't see that on the moon. So those are the two examples where really I think the planetary community seems to have settled that Mercury does have water in those PSRs and maybe a considerable amount. On the moon, it's probably not as great. I mean, we do see evidence of water, but it's or volatiles, hydrogen, but it's not a slam dunk. And this is certainly an example of you can only do so much from orbit, and let's go to the moon and really settle that question.
Great, thank you.